Boom. Hello and welcome back to Calculus1 on this Thanksgiving break, right? Yeah, so people can take break, but we know that breaks shouldn't last forever.
Matt never.
So yes, Matt never sleeps. So we're going to review chapter 4. We're going to take a look at all of the important aspects for exam. This is being streamed, so you can re-watch it if you need to. We start with the so quizzes will start tomorrow at 6 a.m. Exam is, as you voted, next Saturday. And we have exam to be on chapter 4. But what I really want to say is chapter 3 as well. Because all of the techniques for differentiating are in chapter 3. Chapter 4 is application of derivatives. Right, application. So here of derivative of differentiation. You need to know how to differentiate. So it assumes the knowledge of everything from chapter 3, invoking the tangent line, invoking the product rule, quotient rule, chain rule, implicit differentiation. All of those are used in chapter 4. The learning outcomes for chapter 4 are min-max, and then your first, second derivative tests, graphing function by hand, right? Optimization problems, optimization word problems, ties in with min-max, right? Mean value theorem. I'll spell it out. Linearization plus differentials. L'Hopital's rule, and finally antiderivatives. Remember that I said that the numerics, that one section with Newton's method in it, I'm not inclined to put that on the exam because it's calculator heavy and you just sit there and punch numbers forever. The computers do a much better job than you punching numbers in the calculator. So these are the learning outcomes. And I'll write in blood here. Know how to take all derivatives from chapter 3. That includes product rule, quotient rule, basic, chain rule, implicit, and everything else. Where I say linearization, this guy here is your tangent line. Now, whether you're going to memorize the formula for linearization or you're going to use the tangent line from chapter 3, I don't care. The linearization formula is just nicely packaged tangent line. So that's that. So whether you're going to learn the LX formula or you're going to use the differentiation, tangent line, whatever. Just get it right. Now, I also mentioned at one point that the graphing problem will be split over 4 problems, which includes the first 3 together. So min-max problem is when you find critical points and then you figure out whether that's a min or a max. First and second derivative test talk about concave up, concave down for the concavity. For second derivative test, increase or decrease on the first derivative for the first derivative test, and then graphing functions using all of the stuff that you found together. So for graphing functions, we haven't learned anything new. You took x and y intercepts, which is algebra, domain, which is pre-calculus, asymptotes, which is Calc1, right, chapter 2, first and second derivative test, which is from chapter 8. You took all of those concepts and made a shopping list of things that you have to find. And once you have those, you graph the function by hand. So that's what happened in chapter 3, so in section 3. So the way I'm going to give a graphing function is I'm going to give you all of the information in a chart. I will tell you the intervals on which the function is increasing and decreasing and all that kind of stuff. And you are just supposed to graph the function looking at the data given to you. So those are the things that you are going to do at the right. Those are the things you're going to do for graphing. Optimization, word problems, right? You have to model. And then mean value theorem, you have to know the formula. The concept is that average average of the function is equal to the instantaneous change, right? Average change is equal to instantaneous change at least one spot if continuity and differentiability are present. Linearization I already talked about, it's a tangent line. L'Hopital rules, you have two indeterminate forms, 0 over 0, infinity over infinity, and then you have all the other ones that have to be transformed into that. And finally, integrals at the end. So let's start by graphing a function. Pick one of the problems from the textbook, I guess, and then just go through all of the aspects. And as we go through that one problem, we will cover first derivative test as well and the second derivative test, and we will also cover the min-max. Then we can move to word problems. If I could log in, that would be awesome. There we go. So we're going to jump into graphing. I'm not sure what we did in class exactly. I know we did some. Let's try. Well, let's go with 24. I'm sure that we haven't done this one. X minus 3 times x to the 2/3. So in order to graph this, we have to go through the entire shopping list of things. It's a cube root. Cube root does not have a vertical asymptote. Therefore, domain is all real numbers. So we are not going to have partitioning with vertical asymptotes because there are none. X-intercept is calculated when we set x minus 3x to the 2/3 equal to 0. Now, what you can do here is you can factor out x, or you can make these two guys equal to each other. So whatever makes you happy, but if you factor out x, you get 1 minus 3x to the negative 1/3 equal to 0. So if you multiply back, you get everything exactly as is. And now you set x equal to 0, and you set 1 minus 3x to the negative 1/3 equal to 0. So this becomes 3 divided by cube root of x equals to 1. And when you cross multiply, cube root of x is equal to 3, from where x is equal to 3 cubed, which is 27. So it appears that I have two x-intercepts. So one is 0, 0, and another one is 27, 0. Now, 0, 0 is also the y-intercept at the same time. Anytime you get 0, 0 for x-intercept, it's immediately y-intercept right away. Asymptotes, Havasa, right? And that would be none across the board, right? Oh, yes. Make sure that program crashes 15 times. Horizontal asymptote, vertical asymptote, slant asymptote, none. So we are through with the domain, x-intercept, y-intercept, and we are through with 3 asymptotes, so it's time for the first derivative test. So we will take the first derivative, f of x prime, and that is 1 minus 2x to the negative 1/3 because you had 3 times 2/3 x to the 2/3 minus 1. So 3 and 3 will cancel, give you the 2, and then 2/3 minus 1 is negative 1/3. We know that we are supposed to set the first derivative equal to 0. That gives us 1 minus 2x to the negative 1/3 equal to 0, which is 1 equals to 2 over cube root of x, from where 2 is equal to cube root of x, and x is equal to 8. This is our critical number. You can find a y value for it as 8 minus 3 times 8 to the 2/3, which is 8 minus 3 times cube root of 8 is 2, squared is 4, so the whole thing is negative 4, and we have the critical point at 8, negative 4. We do the partitioning. We are on infinite domain, from negative infinity to positive infinity. We have no vertical asymptotes, and we have one critical point at 8. So we are to pick 2 test points and check them in the derivative. Clearly, My test points are going to be the points that I can easily compute. So I want the cube roots. So I'm using 0 and I'm using 27 because it's easy to compute square root of 27, cube root of 27. So now, first derivative computed at 0 is 1 minus 2 times 0, or maybe I should just write it as 2 over cube root of 0. Oh, wait. Zero is not a cool value. Huh. I missed that. The what? I missed that. Look, you can write your derivative. Well, I have it here. So if you use 0, because it's in denominator, the derivative does not exist, right? So I actually have to partition at 0 as well. So critical point is there, and at x equals 0 as well, because you can't plug in 0 into the first derivative. It's in denominator. So I have to pick other values, and I will pick 1 and negative 1. Easy values to take cube root. All right, now let's go. The first derivative at negative 1 is 1 minus 2 over the cube root of negative 1. Well, cube root of negative 1 is negative 1, which makes this positive 2, so we get 3. Larger than 0, increase on this part. First derivative computed at 1 is equal to 1 minus 2 over cube root of 1, which is negative 1, which is less than 0. We have a decrease over here. And then we have the 27, which is 1 minus 2 over cube root of 27, which is 1 minus 2/3, which is 1/3, which is larger than 0. So we have increase again. Now what we see is that we have a minimum value at 8. And something that would suggest a maximum value at 0. But we'll have to investigate that more. So now that we are done with the first derivative test, we have all the increase and decrease intervals. We are going to jump into second derivative test. Now the first derivative was 1 minus 2x to the, what was it? Negative 1/3. To find the second derivative, the derivative of 1 is 0, and then 1/3 will drop down and become positive 2/3, because negative 2 times negative 1/3 is positive 2/3. And then x will be subtracted 1, so negative 4/3. When we set this equal to 0, we get x equals 0. And we know that f of 0 is 0. So 0, 0, inflection point. It's not a maximum. 0, 0 is inflection point. So I'll go back and scratch this max out. Now, you might say, but wait, I got this. No. If you remember my first example, a second example I gave you was x cubed, right? And if you remember, first derivative of x cubed is 3x squared. When you set equal to 0, you get 0 on it, right? So it looks like, ooh, we should have min and a max. But then when you do the second derivative, you'll see it's an inflection point. It's not min, it's not max. Now, I don't like the fact that we have an inflection point. Oh, I know what it is. Okay. Now, we have a partition at 0. We are on infinite domain, negative infinity to positive infinity. And we are going to pick two values, well, -1 and 1, because they are very easy to compute. This becomes irrelevant. Now, what you see, guys, here is that you have this fourth power, and a fourth power makes everything positive. So your second derivative computed at -1 is 2/3 1 over -1 raised to the 4/3. You see, the cube root, that a third, a cube root is going to preserve whatever sign you plug in, but the fourth degree will make it always positive. So this is equal to 2/3, which is larger than 0, which means concave up, and so is the other one concave up as well, because, so I'll just put plus minus 1 over here, because it's the same calculation for both. That fourth power, the even powers always kill negative signs if they show up. So there you go. Concave up and concave up. So question is now, can I graph this? Do I have enough information? If not, we are going to compute additional points. So what I have found is that I have x-intercept at 0, 0. And I also have x-intercept at 27. So do I have any other points that I need to worry about or no? That's it, right? Just 27 and 0. So 5, 10, 15, 20, 25, 30. And this is where 27 is. Now, I have concave up and increasing. Concave up and increasing better look like this. Where's my maximum? 8, -4. What? I did a poor job of of drawing this because this has to be a max. Wait. It's a max. Is it a max or a min? Oh, it's a min. Good. Why did I write max? It's a min. Good. So that's the minimum value there. And there it is. So you have this spike at 0, 0. It's not differentiable there. Did anyone verify this on the calculator or the graphing utility? Beautiful. Now, what type of information is given to you to graph? Well, a chart of values is given to you. So, something like this, where I say f prime, f double prime, and then over here is just domain. Some part of the domain, whether it's interval or a point. And then I say, because I worked the problem on the, so this is how I make the exam actually. So I solve the entire problem and I look at this and I said, all right, so they should be able to do this. Now I say concave up and it's broken at 0. So second derivative, right, needs to be positive. So I have 0 as important point. I have 8 as important point as well. All right, cool. So this is what I do. Negative infinity less than x less than 0, 0 less than x less than 8, and then 8 less than x less than infinity. So these are the three partitions. Oh, I need to also plug in, x equals 8 over here. That's it. X equals 8, and then 8 less than x less than infinity. There we go. So now, I tell you that when x equals 8, you have a negative 4, and in a comment section, I write it's a minimum. So this is like a comments over here. Comment section. So now, we don't care what's happening with the function here. I know that the first derivative from negative infinity to 0, it's increasing, so I just put plus minus plus. Obviously first derivative over here is 0 because, so positive, negative, positive. So that means increase, decrease, increase. You need to know that. The second derivative test breaks at 0. So, but it's concave up everywhere. So concave up, concave up, concave up. So there's all pluses, all positive. This is the chart that you get. It says graph. Oh, I also add, I forgot a column, one of the rows. There has to be a row over here for 0, 0. That's x-intercept and the y-intercept. And for 27 as well. Maybe I can write it on the side. Whatever. Plus 0, 0, 27, 27, 0, x-intercepts. Now you all immediately know that 0, 0 is a y-intercept as well. So you get this chart, and you get the empty grid. That's all you need. You will go, all right, these are the points I know. Pook, 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 right? You put the points. Every minimum is a smiley face. Every maximum is a frown. I should put a little frown or a little smiley face. And then you connect the rest. Some of you might draw the line with arrows and concave up, concave down, or you can just look at the chart, whatever you are more comfortable with. But the chart is just a summary of all of the information. If there are asymptotes, I will write the asymptote as well. So you see how I have the line for a minimum? I might have x equals to 3. And just empty everything as just VA, vertical asymptote, right? So that might be given that way as well. So you have the chart, and as you can see, by doing this problem, we review the first derivative test, the second derivative test. We also figure out mean and max because you find the critical point. Set equation equal to 0, right, by finding critical point. And then you have mean or max happen at that point if it's actually a point, which is defined. And that takes care of sections 1, 2, and 3 by looking only at 3. Questions, concerns on graphing? Yes?
When we look at the mean and the max, we don't see the relative maximum or absolute. We just see the minimum or maximum.
Well, now that you have the graph, you know it's a relative, right? You know it's relative because you see that this one, right, will always go down. So all of these values are lesser than -4. So, yeah. Any other questions? All right, so if there are no questions, then we can go on with the next problem. Optimization. So famous problems are farmer problems, where you maximize the area. I'm not sure if anyone worked on the box. I gave you the challenge to make the box, right? Bring it in next class. Yeah, I know, right? Right. With the turkey leftovers.
I think there's one about like a window with light. I don't know if you know about it.
Oh, on the lab?
Yeah,
you're not gonna. If you got 7, it's wrong, right? Because the answer has to be in terms of p, and it's going to be a whole line in your notebook.
It's complicated.
Yes, yes, yes. So have fun with that one. It's going to be awesome. First time I saw that problem on the lab, I was like, what the hell? Nice. Nice. We're gonna go crazy to solve this. But that's okay. You can do it. Nothing that few hours can't accomplish, right? Let's see if we can find problem 15 is just fine, I would say. Of all boxes with square base. The whole box is with a square base and a volume of 100 meters cubed. It's a lot. Which one has the minimum surface area? Which one has a minimum surface area? We learned a very specific way to do these problems. Create a mathematical model using the formulas with the words that are given in the text. There's the word volume and the surface area. And there's a box with a square base. So we use all of these ideas. Box is a three-dimensional object. If it is to have a square base, I can draw a diagram for it. This is the square base, and these are the four sides that you need to stand up, right, to create sides of the box, and then you need the lid, which is the top. So it looks like this. You don't believe me? Cut it out of paper at home and fold it. So this is what it looks like when the box is unfolded. Three-dimensional box is unfolded into a 2D shape. Now we see that these guys are x and x, and the height of the box is y. They're talking about the volume. Volume is area of the base times the height. The base is x squared, and the height is y, and that's 100 meters cubed. So yay, we have our constraint equation that relates variables x and a y. And now the surface area will have the areas of these 6 rectangles added together. Well, you have 2x squares, which is the bottom of the box and the top of the box, and you have 4xy rectangles on sides, which creates the walls. We are sitting in one of those boxes right now. Your ceiling and the floor are the square, right? Base and the top, and you have 4 walls. They're all x times y. So if the dimension this way is x and dimension that way is the same as x, this is a different dimension y. So you have x times y on that rectangle, and you have 4 of those. If this is x and that's x, then they are the same, right? Because they share common y there as well. And we want the minimum. Why do you want a surface area of the box to be a minimum? Why not a maximum?
Airports go to a plane or something.
What?
For travel, they want small boxes sometimes.
Well, they don't go by surface area, they go by the volume. They go by dimensions as well. Why do you want the minimum surface area? Why? Why minimum surface area?
Let's say you're throwing these boxes to a far distance. You want to make sure friction plays a minimum role in how far you throw air resistance.
You're gonna put this in a bigger box and ship it. So yes. I'm sorry? There is our packaging engineer. Nice. The minimum surface area of this box over here means the less cardboard. Remember, I am making 100,000 units. If I save $2 in cardboard on this box, that is $200,000 savings across the entire production. Very good. So, reducing the surface area while still being able to plug in the printer or whatever I need to put in the box, right, means lesser cost of the material. You want to maximize the volume to stuff as much stuff possible into the box. But you want to minimize the surface area so that you use less materials to make it. And with that, obviously, save the most amount of money that you can. By the way, that box is sitting there for years and years. This Dell printer, that's the HP printer from 1973. That box is still there. I don't know why. So we are having our two equations. This is the important part, right? The top equation in the bubble is called constraint equation because it puts constraint on the relationship between x and y. And the bottom one is objective equation. This is what we want to calculate. We want minimum area. So it's called. So now, once you do this, the rest of the problem is mechanics. It's not thinking, it's just doing. You always go to your constraint equation and you solve it for one of the variables. In this case, it will be a y. So you always go to your constraint equation and solve for one of the two variables. Whatever is easier. And then you take that and you plug into objective equation, obtaining 2x squared plus 4x times 100 over x squared equals to a minimum, which gives us 2x squared plus 400 over x equals to a minimum. And now we differentiate in respect to x because we are looking for the horizontal tangency. Remember, right, you are looking for a critical point. And this minimum, which is a number, right, minimum surface area of 37. It will go to 0 when you take the derivative of that. It's a number. So we have 4x minus 400 over x squared is equal to 0 when you take the derivative. Right? Okay. And now 4x equals to 400 over x squared. Cross multiply, you have 4x cubed equals to 400. X cubed equals to 100. And finally, x equals cube root of 100. If it was 1,000, the answer would be 10. It's not 1,000, it's 100. So leave it there. So we have that x is equal to cube root of 100 meters. Not potatoes, meters. And then you have the formula for y. Right here, formula for y. So y is equal to 100 over x squared, which means cube root of 100 squared. Now this is 100 divided by 100 raised to the 2/3. When you subtract 1 minus 2/3, you get again 1/3. So 100 to the 1/3, which is again cube root. So dimensions, yeah, cube root. So dimensions are cube root of 100 by cube root of 100 meters. So it's actually a cube. It's a cube. So it's very interesting. Cube is a special object, guys. For a given volume, cube will have minimum surface area. For a given surface area, cube will have maximum volume. That's how it works. We talked about the farmer problem. And we know that the farmer has fence. So 200 yard of fence, wants maximum area. So what are the dimensions? Now, I want to set up a really crazy situation, right? So because we've seen the cheap configurations earlier. So let's say that the neighbor's property goes this way. That's a neighbor. The farmer wants to set up his stuff right here. So this over here is the pre-existing fence from the neighbor. Or the government, or whatever. So farmer needs an X, a Y, and a half a Y here. That's all he needs. So now, the perimeter equation is X plus Y over 2, and then needs to be 200 yards. So this is your constraint equation. And the area is X times Y, which we want to be max to get, right, the most out of the fence. Solve, as always the same. Solve for a variable, in this case X equals 200 minus 3/2 Y, because you have a Y plus a half a Y is 3/2 Y. And now, when you do that, plug into the objective equation. So X is replaced with 200 minus 3/2 Y, and then times the Y is equal to a max. Distribute Y, and hit that with the derivative. And now it's a dy derivative because we are with the variable Y, and we are going to figure out Y first, and then go back, figure out the length of X. So the derivative is 200 minus 3Y is equal to 0. From where clearly Y is equal to 200 over 3. So Y is 200 over 3. And now we feed that into the Y right there to find value for X, which is 200 minus 3/2 times 200 over 3. These guys cancel, and we get x is equal to 100. So max area obtained with dimensions 100 by 200 over 3 yards. So x is 100 yard. So the farmer is going to go and calculate from the existing fence 100 yard this way, right? Start anchoring the fence, go all the way down for 200 divided by 3. So that's the first number you can divide evenly is, well, you can do 2 or 1, right? And then subtract third, whatever. Wherever you make it. And everything has to work out. It's perfect. So those are the word problems. Generally, they're all the same in terms of methods of solving them. Find the constraint, find the objective equation, solve n for a variable in constraint, plug in objective to eliminate the other variable, and then whatever variable you're left with, you take the derivative in respect to that variable, and you go from there. So it's a very systematic work, and I hope you will practice. And again, if you have any issues, guys, this is about half of the class here, or a third, or half, yeah. But if you have any issues, stop by at my office hours the next week. You know that I have 5.5 hours of office hours during the entire week, so stop by and ask questions. The next one is the mean value theorem, I believe, or linearization, whatever it was. But the mean value theorem says that the average rate of change, which is f of a minus f of b over b minus a, has to be equal to the derivative of some value c, where this c is between a and b, and the function f of x is continuous and differentiable on ab. So that's the mean value theorem, and now you come up with a function and a range, and you ask yourselves at what point, right, do we have this. So maybe, I know we did an example, so I don't want to do the same one. No coughing. We did ln 2x from 1 to e. Maybe I can find in a textbook a trig problem that you can, because I know how much you adore trig. I don't want you going home disappointed. This is MVT, mean value theorem. So which problem should I work on? I already did 20. Anything else? 17 to 24? All right, I guess moving to the next concept. 18 it is. f of x is equal to 3 sine 2x, 0 to pi over 4. Sine function is continuous everywhere. It's a theorem we learned, chapter 2. And it's differentiable. No vertical asymptotes and stuff. So it's very differentiable everywhere. So let's take a look at this. You compile the left-hand side by simply computing pre-calculus and algebra. So what do we have on the left-hand side? We have f of b, which is 3 sine of 2 times 0. No, b is pi over 4. Pi over 4 minus 3 sine of 0, because 2 times 0 is 0. Divided by pi over 4 minus 0. And this needs to be equal to the derivative at c. Now the derivative of, you can find the derivative in terms of x on the side. It is 3 copy, and then the derivative 2 jumps out. So 6 cosine 2x, right? That will be the derivative. Because the chain rule will kick 2 outside. There is already 3, so 3 times 2 is 6. Derivative of sine is cosine, keeping the same argument. So this is 6 cosine 2c, right? Because you can see that in the formula, c is plugged into the derivative, not x. So that's why we put, instead of 6 cosine 2x, we put 6 cosine 2c. And now we compute everything. Sine of pi over half is 1. So we have 3 times 1 minus 3 times 0 over pi over 4 is equal to 6 cosine 2c. Well, 3 times 1 is 3 minus 0 is still 3, and times the 4 from the bottom is 12 over pi is equal to 6 cosine 2c. And now you will divide both sides by 6. Now our goal is to solve for c, right? We are looking for the point C, which is on x-axis, where the instantaneous rate of change and average rate of change have the same value. So when I divide by 6, I get 2 over pi is equal to, leave some space, cosine 2c. You hit both sides with the inverse cosine to kill the cosine. And you get that the 2c is equal to the cosine inverse of 2 over pi. Divide both sides by 2. And there's your value of c. It's 1/2 cosine negative 1, 2 over pi. So that is the value of c. Now you can go to your calculator and punch these things in and get the decimal. I don't care. You might. So if you want to go and get those decimal, fine. Procedure is very systematic. You have your a and b, and obviously if you don't know the formula, you're just dead. So, I mean, in that problem, you're dead. So that was that. I want to challenge you in this room to compute. So use linearization or differentials to approximate square root of 82. Now, when you're going to do this with linearization formula or the tangent line, as Nike would say, just do it. There are two ways to compute this. Well, there are three ways. You take a calculator and done. But then let's say you are out with your friends and someone mentions, what do you know? Bring the napkin. Square root of 82. Let's see. So value A will be 81 because that's square root I know. The function is square root of x, and its derivative, which I will need, is 1 over 2 root x. Now, if you did not memorize the linearization formula and you do not want to memorize linearization formula, you will use tangent line. I, in my infinite wisdom, know linearization formula, which is f of a plus f prime of a times x minus a, and I will plug everything into this linearization formula. So f of a would be the square root of 81 plus 1 over 2 square root of 81, and then x minus 81. So L of x is going to be square root of 81 is 9 plus 1 over 18, because 2 times root 81 is 2 times 9, which is 18. And then I have x minus 81. So this is the linearization. I could go and get it into y equal mx plus b, but to be honest with you, I don't care to do that now. What I want to do is I want to approximate 82. So instead of computing square root of 82, I will compute linearization formula with 82. So that's 9 plus 1 over 18, 82 minus 81 is equal to 9 plus 1 over 18 times 1. Right? So this is 9 and 1/18 as a mixed fraction. All right. So we can calculate that 1/18. So what is the 1 divided by 18? It's so square root of 82 is approximated by 9, well, 9 and 1/18, which is approximately 9.05555 going forever. Now, calculator says that the square root of 82 is approximately 9.05539. So we see that we are 2/10 of a cent off. 2/10 of a cent. We're off 2/10,000ths. So that was a pretty good calculation for square root of 82 without a calculator. We are really close. Now the other way is to use differentials, where delta y is approximated by dy, which is equal to f prime of x times delta x. Now we know that delta x and dx are the same thing. So instead of approximating a number directly, we can approximate the change as the number changes from 81 to 82, which creates this delta x, which is 82 minus, well, 81 minus 80, no, I was right, 82 minus 81, wow. 82 minus 81, which is 1. We still have that our function f of x is the square root of x. That doesn't change, the same problem. And the derivative obviously can't change either, because the same input function. So 1 over 2 root x. So now, the change in y is approximated by dy, which is equal to 1 over 2 square root of 81 times 1. And that's that good old 1 over 18 we've seen before. So now square root of 82 is approximated by square root of 81 plus the change, which is dy, and the square root of 81 plus 1 over 18 is 9, and 1 over 18, and it's the same as the other one. Now, people usually get confused on how to put the problem together at the end. Yeah, you remember that the delta x is the difference between the new and the old, and right, all this kind of stuff. You remember all. It's what happens at the end that people don't get. Learn to read the formulas, read them aloud, and listen to yourself talk. The square root of 82 is approximately equal to the square root of 81 plus the change between root 81 to root 82. Does that make sense? I can't compute root 82, but I can compute root 81. Now, since I changed my x from 82 to 81, there also has to be a change in y values that it produces. We are computing with this method that change, and that change is what we either add or subtract to the one that we can compute to approximate what we want to compute. So, square root of 82 is approximately equal to square root of 81 plus the change in y, and that's that 1 over 18 which we computed from the differential. So differential approximates the change in the y value of the function, and we use it we use that dy change to fix. Should I use that word now? Fix the calculation so that we can have a good approximation for square root of 82. Bueno? Good. So that was a whole bunch of linearization, word problems, and things. We have two extremely important things left, and those are obviously L'Hopital's rule and integration. So I want to go and talk about integration first, because that one is going to be carrying on to chapter 5. So integral of a constant dx is cx. Shouldn't they use the c there? How about k? And then plus c. Integral of x to the n dx is x to the n plus 1 over n plus 1 plus c. Integral of 1 over x dx is ln absolute value of x plus c. Don't forget the absolute value. Integral e to the x dx is itself e to the x, but you must put plus c. And then we have integral of we have all the trig, but do we have anything else other than trig? We had constant, we had polynomial, we have 1 over x, we have e to the x. Integral of ln x is studied in Calc 2. It's not a basic integral. So apart from trig, are we missing anything? I don't think so, because this one over here takes care of x squared and square root of x and 1 over x squared. So depending on, you know, so that one takes care of all of those. We have the constant one on top. We have the 1 over x, which creates ln x and the absolute x, and we have e. So all that's left is trig. So integral of sine x dx is negative cosine x plus c. Integral of cosine x dx is positive sine x plus c. And integral of cosine. So okay, so we have that. So now we have secant x tangent x dx is equal to secant x plus c. The integral of cosecant x cotangent x dx is equal to negative cosecant x plus c. Then we have the integral of secant squared dx, which is tangent x plus c. Integral of cosecant squared it's negative cotangent plus c. Do I have all of them? 1, 2, 3. Yep. Cotangent x plus c. So what is the integral of x to the 6? Quickly. What is this? Thank you. You can also write it this way. How about the integral of 4 over x cubed dx? So what should I do first? Do what? Yeah, but what number am I plugging into a formula? But this is not a single, this is cube. Yes, so 4 integral x to the minus 3 dx, and then you use the formula for x to the n, which is negative 3. This works only when you have 1 over x and nothing else. No exponents, nothing. So this is 4 x to the negative 2 over negative 2 plus c. So the answer here is negative 2 over x squared plus c. Cool? Does this make sense? So we have to rewrite. And then it would work. Yes?
Do you have to do the implicit functions, like getting derivatives of implicit functions?
No. No. How about, I was about to write 4 again. Let's go with 7. Divided by the fifth root of x dx. What should I write? 7 integral? Yes. X to negative 1 over 5. So now we do plus 1 everywhere. So it's x, when you do plus 1 you get 4/5 over 4/5 plus c. And now you fix the coefficient. So that's going to be 35 over 4 x to the 4/5 plus c. Nice. Alright, so now how about integral of x cubed plus 3 e to the x minus 1 over x, all that in parentheses dx. Remember, when you have multiple terms, you have to put the parentheses around, because that dx needs to multiply every term. All right, so these are all basic derivatives, right? You just write the answer. What's the answer? X 4 over 4. That stays, and then absolute value of x. That's extremely important to have the absolute value there. Now, if you remember, I said that integral e to the ax dx would be e to the ax and then over a plus c, and let's say integral of cosine bx dx is equal to sine bx over b plus c. So you can have those as well. We are going to cover that in detail in 5.5 using something that's called Au Substitution. You will understand why these work the way they do. Just to put the derivative formula on the side, the derivative of e to the ax is a e to the ax. So the derivatives multiply the constant and the integrals divide by the constant as you put them together. Good. And the last part that we have are the L'Hopital rule limits. We spent more than 2 hours last time talking about those. We've seen that they progress from the basic form, which was indeterminate form 0 over 0 and infinity over infinity, to 0 times infinity, where you use that algebraic manipulation, to infinity minus infinity, where you involve factoring, to, at the end, logarithmic methods. So, for L'Hopital, we have the basic case, which is 0 over 0 or infinity over infinity. And then we jump into the next level up, which is 0 times infinity, where we use f equals 1 over f to switch it into the basic form. And then we have another upgrade, which is infinity minus infinity, where we have to use factoring. Then f equals 1 over f. And then we have 0 to 0, 1 to infinity, and which one? 0 to infinity, right? And we use logarithms. So the procedure is ln both sides. You also want to memorize that e to the a is given by the limit x goes to infinity of 1 plus a over x to the x. You want to memorize this because you really don't want to be, cranking ln and L'Hopital calculation every time you see this, and it's frequent in your future classes. So just, bite the bullet and memorize it. The most basic case was limit x goes to 0 of sine x over x, which we know it's 1, but if you plug in values you get 0 over 0. So you can't compute by plugging in. You unleash L'Hopital because you have 0 over 0. And that changes the problem, but it keeps the same answer. So the derivative of sine x is cosine x divided by 1, 1 over 1, and the answer is 1. This was the first exercise I worked out to emphasize the procedure. And the procedure is you plug in whatever x goes to, you plug that in, and if you get infinity over infinity or you get 0 over 0, you are allowed to use L'Hopital's rule. Now if you get anything else, you can't. That's it. So there's two indeterminate forms, 0 over 0, infinity over infinity. And yeah, that's it. Now let's see what else we can find. How about limit as x goes to 0 of x squared times ln x. Right, so if you are looking into this problem, you will say, all right, I have 0 times negative infinity, because the ln graph looks like this. So as x goes to 0, the y value goes to negative infinity. So this is one of the 0 times infinity problems. And we know that the trick for 0 times infinity problems is to pick one of the functions and write it using the algebraic manipulation. So it's going to be limit x goes to 0 of ln x divided by 1 over x squared. So now when you plug in, you get negative infinity, you get positive infinity. So it's infinity over infinity, which means that you are okay to use L'Hopital rule here. So it's a limit x goes to 0. And now we're taking independent derivatives. So on top I have 1 over x. The derivative of ln x is just 1 over x. And the derivative of the bottom is going to be negative 2 over x cubed. So now work out all of the algebra here. And what I get is x cubed divided by negative 2x. Now that cancels. And I get limit of negative 1/2 x squared as x goes to 0. And now when I plug in that 0, I get a big fat 0. Then the problem is solved. The more interesting cases are the ones that we have for to use the linearization, to use the logarithms for. Let me see if I can find one of those puppies. So limit x goes to 0 of 1 plus 4x raised to the 3 over x. So what you do is you set this equal to y and you ln both sides, because that is the way to peel off the exponent. So now what you have is ln y is equal to limit x goes to 0, and now you have 3 over x times ln of 1 plus 4x. And now if you compute the values, you have infinity times 0. Because 3 over 0 is going to go to infinity, and ln of 1 is 0. So now we use the trick that f is equal to 1 over f. Blessings. We have ln of 1 plus 4x stay, and on the bottom we have 1 over 3 over x. So now when you try, 3 over x will give you infinity, but 1 over infinity gives you 0. So denominator is 0 and the top is 0. But we can, before we do that, we can still simplify this, at least the denominator. And you have x over 3 in denominator. So now it's even easier to see that it's 0 over 0, because you have 0 divided by 3, which is 0. Now we use the L'Hopital The derivative on top is we copy 1 plus 4x as is and put its derivative on top, which is just a 4. And on the bottom, when we take the derivative, is just 1/3. Derivative of x is 1, so 1/3. And we simplify this, so it's going to be 12 over 1 plus 4x. So the answer is 12 for this particular limit as x goes to, oh no, sorry, that's ln y is 12. Yeah. ln y is 12. And then we e both sides, and now we're done. There we go. So y is equal to e to the 12th. Wow. So limit of 1 plus 4x raised to the 3 over x is equal to e to the 12th as x goes to 0. Now, before you storm out, I want to try to solve the same problem using Au substitution. So my problem is the limit x goes to 0 of 1 plus 4x to the 3 over x, and me being me, I think that we can actually change this by saying u equals 1 over x, from where x is equal to 1 over u, right? If you flip it around. So now, when you plug all of that stuff in, you get the limit 1 over u goes to 0. Well, that's weird, but we'll deal with that. And then I have 1 plus 4 over u, and then 3u in the top. Now this one over here, 1 over u going to 0, if the only way for 1 over u to go to 0 is if u goes to infinity. So we are rewriting this problem as u goes to infinity, and then you have 1 plus 4 over u to the 3u. Do you see the definition for e? Both of these guys go in the exponents. So we have equals to the limit, I don't need the limit anymore, equals just e to the 12. And maybe I should circle 12 and circle these two guys, because that's where it comes from. 3 times 4. That's it. So I will see you all next week. I guess it's the exam. The quizzes start tomorrow. So make sure you do those, and I'll see you soon.